Yeah, so welcome back to the Four Methods for Software Engineering lecture. Last time we started looking at linear temporal logic, or temporal logics in general, and then specifically at linear temporal logic. And we looked at some formulas and what does it mean for a model in a certain state to satisfy some formula. We first started by looking at individual computations, so just one trace starting at some state, going through an infinite sequence of going through the states, and then we looked at the labels of those states, and that's what these formulas are defined over. That's how we defined the satisfaction of a single computation. And then we said, well, we can also look at all computations starting from one particular state. And this makes a lot of sense if we want to verify some hardware or software system, because we want to say, if this system starts in a particular state, do we want to guarantee, or how can we guarantee that, for example, it never deadlocks, or that it never gets into a state where both traffic lights are green at the same time? And then we really want to verify it for all possible successors of any states, so all computations that could happen in the system. There might be multiple, because it might be some variables or some labels here are actually controlled by the environment. So is there a car coming? Is that car driving? Stuff like that would usually be something that you sense from the environment. And then there are some variables that the system can control accordingly. So for example, setting the light to green or red. And we want to make sure that in whichever way it controls those states, we guarantee some properties. And these properties we would write as LTL properties. And we looked at these properties and which statements are true and false the last time. But we might also be interested in the specification part. So the specification part are the LTL formulas. And we might ask for something like equivalence between formulas. Now, how would we define that? Because what we have is satisfaction of traces, satisfaction of models. And now if we want to talk about equivalence, we're actually asking, are these two formulas equivalent such that all paths of any two models, if the path satisfies the first formula, then it also satisfies the second formula. And this is for all models M. We can pick all paths. So it's like for all models, for all paths, the two formulas, they always disagree whether the path satisfies the formula. And then we can say that those two formulas are equivalent. There are some equivalences that we know from propositional logic. So does anybody know what this kind of equivalence here is called? The negation of a disjunction is a conjunction with a negation of the two elements. Anybody knows what this law is called? Some logic, propositional logic, but it also holds in this temporal logic extension that we have. So this is De Morgan's law. There are some De Morgan's laws, like also the outer negation of the conjunction. That's the negation of the two of the disjunction of the two elements in a disjunction. And then there are other equivalences that we have already seen. So of course, those equivalences from propositional logic, they will still hold. And then there are some other equivalences that were more or less defined equivalences, right? Because we said we want this operator that eventually psi is true. So after some finite amount of time, psi is true. And we said, well, we can simply define this by saying we don't care what happens until psi holds. And this until always had the guarantee that after some finite amount of time, there's some index where psi actually will hold. And similarly for the globally, we said we don't want that sometime in the future psi doesn't hold anymore, which means it will hold forever, and that's how we defined the globally. So these are also some equivalences that we can work with. So if we want to determine for two formulas whether they are equivalent, what we could do is we could see whether we can only using equivalences translate one into the other. And some more equivalences. So we have some properties about negation again. This eventually and globally, or finally and globally, they are dual of each other. So the negation of globally psi is eventually not psi. So we basically can move the negation in, and then we have to flip the operator from globally to finally. And it works also the other way around if we have not finally, so not after some finite amount of time. This basically means we have globally not psi. So there's no point in time where psi will hold. That's what the left side says, and the right side basically says always psi is false. So that's the same meaning. And then what about next? So next is actually dual to itself. If we say next or not next psi holds, then it's the same as saying next we don't have psi. So yeah, you could also unfold these. So if you remember what psi, what the next means, the next means that taking the suffix starting at the second state, then this needs to hold, and you can, well, unfold the same here, and you have the negation around it, and then after basically unfolding this, they both are the same on each side of the formula. And so these would be dualities, but then also we have some distribution laws, like you know from simple arithmetic, but here the operators, they distribute differently. So for example, if you have finally psi or phi, this is equivalent to we either have finally psi or we have finally phi. The same works differently for globally, because for globally we need the end. If we have for every point in time we have psi and phi, that's the same as for every point in time we have psi, and also for every point in time we have phi. Now the question, if we have this f distributing over the disjunction, what about conjunction? Does the same work also for conjunction? So what would it mean if it distributes over conjunction? This would, let's write that down. So we said this distributing over some other operator. That's not the best one. Okay. So we try this one. So distributing over some operator. This looks a bit flipped. One more. No, what's the autofocus? Good. Come on. Yeah. Good. Okay. So the question was whether finally distributes over conjunction. So let's say finally psi and phi. Is that, it's not really better. Okay. Is that the same as finally psi and finally phi? So either we unfold this, what does it mean to have finally, or we can rewrite finally as the until, right? Then we have something even longer. Then we can try to write the until as the meaning of there exists some index, right? That's one way if we, well, yeah, carefully want to prove it step by step. Another way is if we see, well, it's not true, then we could, how could we show that it doesn't work? If it doesn't work, so if it works, it means that for all models and for all paths, we have that those two agree in terms of the satisfaction or non-satisfaction. So what happens if we find at least one path where they do not agree. Then we have shown that they're not the same. So we need to find a model and a path in that model where they do not agree. Can we construct such a path and model? So we need at least one state, right? So let's do a model that's a transition system. So let's have one state. Now we have something with finally, right? And we probably need something which is labeled differently. So let's maybe take another state as well. And then we need always infinite traces or infinite computations. So let's create a loop. Now, where do we want to start? Doesn't really matter in this model, right? Because it only has two states. So we will repeat the same thing anyways. So let's see, which way is it more interesting? So if we have some state where both are true. So let's say this state would have labeled psi and phi, right? Because then this left side here is satisfied. So let's label this with psi and phi. Then, well, there's no way around visiting this state, right? And in this state, we have psi, and in that same state, we would also have phi. So this means that the left side basically implies the right side. So whenever the left side is satisfied, also the right side is satisfied. So this is not going to help us because there it looks like they are fine. They are, well, in one direction, they are equal, so that whenever this one is satisfied, that one is also satisfied. Question is, does the other direction also work, right? Because we want to say that whenever that thing is satisfied, that thing is satisfied, and whenever the right side is satisfied, the left side is also satisfied. So we need to construct something that satisfies the right side and not the left side. So how do we avoid satisfying the left side if we never have psi and phi in the same state, right? But we also want eventually psi and eventually phi. So we need them in some state. We need each of them in some state. So let's put psi in one state and phi in the other state. Now, well, I mean, usually we don't label it with formulas, but you could imagine that here we're just asking for any formulas, so it could be atomic propositions, right? So it doesn't matter whether I label it with A and B or with psi and phi, right? They could be atomic propositions. And if it doesn't work for atomic propositions, then it doesn't work for all formulas, right? So now the question is the right side satisfied by some trace generated by this model? So what would be a trace? For example, psi, phi, psi, phi, psi, phi, right? That's infinitely repeated. That's a trace. That satisfies eventually psi, yeah? And it satisfies eventually phi. Does it satisfy eventually psi and phi? No, because they are never true in the same state. So this is never true in the same state. So now we have shown an example that these two are not equivalent because we have found a model and a trace, and that's enough, where one is satisfied and the other one is not satisfied. Okay. So yeah, we also had this model actually where it was the same. That's the model that we used before, and if you pick P and R as the individual atomic propositions, then you would have from S0, you could have eventually P, and you could have eventually R by going in the, well, left side loop, but you would not have P and R in the same state ever. Well, or yeah, definitely not in this trace, right? So this means they would not be equivalent. Okay, but you don't have to make such complicated models. You can basically just find very simple ones. Good. Then there are some more LTL operators, And again, these additional operators, they are defined based on abbreviations of existing ones. So here, there is something called the weak until. What this means is it's basically the real until, the strong until that we always knew, where phi has to hold after some finite amount of time, right? That's the strong until. But the weak until says, well, it's also fine if just psi holds the whole time and we never see phi happen. So the strong until or the regular until would say psi needs to hold until we have phi happening. But the weak until says, well, actually, either phi happens sometime in the future or not, but then if it doesn't happen, we need to make sure that psi stays true the whole time. So yeah. And then there is another operator, the release, which is like the dual of until. So the negation of the release operator would simply be the negation of the until, but also pulling the negation into the individual formulas of the until. And that's the same as the weak until. So this phi releases psi means that psi might hold forever, or we will see that phi happens together with psi, and then it could be, well, the end, like this until. This could be the thing that we finally eventually reach, or simply psi holds forever. So this means that we know that phi will hold, and then at some point in the future, phi will hold, and psi will hold. Now it's the right side of the release operator. Psi will hold, and at some point in the future, phi might like join psi to also hold in a state, and then we don't care what happens afterwards. Or if it doesn't happen like that, then we need to make sure that psi remains true forever. Okay. This was all about the future, but there's also a past, right? And sometimes it might make sense to talk about the past. So there are also past LTL operators. They're not so common, but they're also implemented in this tool that we're using. And there is some work that has shown that past operators are really useful because they allow you to express some properties much shorter than with future operators. So it turns out that past operators do not add expressive power. So everything you can express with past operators, you could also express with future operators. But sometimes the past operators allow you to have exponentially shorter formulas, which is really, a strong property, right? You might have to write an exponentially long formula to express what you can express with past operators only with future operators. Okay, so the Y operator, that's like the X operator, but it's now previous. So X means in the next state, and previous means in the previous state. And then we have historically, that's similar to the globally, it's the analog of the globally. Globally means from now on in the future, and historically means up until now, the whole past up until now. Then once, that's a bit like the eventually, because it means that once in the past, something must have happened. In eventually, we say that sometime in the future, something must happen. So they both are requiring that it actually did happen. And then we have since, that's the analog of until. So if you basically, what does this analog mean? If you basically take the timeline, usually at time 0, to the one side, you extend the future. And to the other side, you would extend the past. And it's like if the right side of the future satisfies the psi until phi, then if you would mirror it into the past, then this is the psi holds since phi was true. So this is the thing that must happen once, definitely in the future for the until, and that's the thing that since that happened in the past, this thing now holds true. So this is the analog by basically mirroring it in the time axis. So the eventually means that sometime in the future we have the event psi happening, and the once means that sometime in the past there definitely was this psi true. Similarly for the globally means, well, everything in that future direction must be satisfying psi, and the historically means everything in that past direction must satisfy the psi. There's some, well, of course, difference that the future usually is infinite and the past can only be finite because the system started at some point. And you would usually mix all of these. So they have some, let's say, maybe not so intuitive behaviors in the initial state. So if you would just write previous phi, I think that's false, because if you just write something without nesting into any other operators, it means you evaluate it in the very first state, and the first state doesn't have any past. So that's why something like that has, well, some not necessarily intuitive behavior. But if you say that eventually something happens, which implies that once something else happens, then, and you nest the once in the eventually, then this suddenly makes sense, because once you are, well, the eventually is sometime in the future, and then it evaluates the once, so the past formula, over everything that has happened until that eventually in the future. So usually they are nested within future operators, and you can use future operators without past, but it doesn't make so much sense to use past operators without future. Unless you do something which is not about, let's say, model checking. If you do, for example, runtime verification, where you want to make sure that some system satisfies some properties, then you always have only the past, right? Because you only observed what has happened in my system so far. So you're analyzing some logs in a data center, then everything you analyze is basically the past, and then you can evaluate those past operators at whatever point in time you are. And then if you want to use future operators to analyze something that is only finite, you have to come up with clever ways to define the meaning of future operators on finite histories, which people have done because people want to do runtime verification. That's a big field as well. But then the definitions have to be a bit different, because, for example, the until might not have been satisfied yet. So do you say it's false because the thing didn't happen in the future? But the future might still be ongoing. So you can't completely determine that the until is false. If the thing that the until requires to hold was true sometime in the past, you can say the until is satisfied. But otherwise, you don't know. So you have to now work with is violated or is satisfied, or you don't know. Same for if you say something always holds. If it's violated, you can say it's false. If it hasn't been violated yet, you don't know if it will always hold in the future. So you don't know. And you can never really say it's true, because for that you would have to know all the future, which you usually don't know in runtime verification. So there are then some different definitions. But what we will do is we will usually analyze those kind of systems that we model in a particular way, so that we can fully analyze them with all their future. Okay, then let's look again at some equivalences. So this is a bit like the thing that we did with the eventually, where we wanted to see, does the eventually distribute over the conjunction? So here we have two other formulas. We have globally finally P or Q, and we have Q and globally P. Now, here this equivalence is basically just the thing that we did on paper. And then to do this equivalence, we could first solve implication in one direction, like we did before, and then implication in the other direction. And if implication works in both directions, then we know that they are equivalent, right? So let's see, which one do you want to start with? Let's not start with this one, right? That wouldn't make so much sense. Let's start with one of the implications. Which one is easier? Okay, let's start with B and see if we can either prove it or disprove it by giving an example where it breaks. So this means B means we already have globally finally P or Q. And then does this mean that we have initially Q, right? Here Q says initially Q and globally P. Well, how do we show that something satisfies this one but not this one? This one requires initially Q, right? So if we find a system that doesn't have Q in the first state, we could show that this one is violated, right? So can we find a system that doesn't have Q in the first state but still has globally finally P or Q? Yes. We could even find so can you give an example of a system? Well, it has, yeah, that has no Q at all. Yeah, so let's do a system that has no Q at all. So let's do, for example, a system that only has P. And then we need, of course, infinite traces. So let's do that. This one has then, of course, the P and so on. So like a computation that would be this. And the question is, does this satisfy globally finally P or Q? Yes, because in every state, there is some future state where P holds. And yeah, that means that this thing is true. Now, the second one, does it satisfy Q and globally P? No, because Q never holds, so Q also doesn't hold in the initial state, right? Okay, good. So we have shown that this is an example where the B doesn't hold, right? So B is false. This implication in B does not hold on this particular trace. So we already know the answer to A, right? Because we know A cannot be true. They can't be equivalent because we found a trace where they disagree. Okay. Now, what about C? In C, it asks, can we find a model that satisfies psi and violates phi? So we can't violate this implication. How? So if this one holds, will this one also hold? So this one says we have Q and globally P. So this means that every trace that will satisfy the left side, so let's say we write it as a kind of a table, Q and P, and then what do we know about, so the formula was Q and globally P, right? So Q and globally P. What do we know about P in the first state? It needs to be true, right? Because it says globally P. So this must be true. In the second, must always be true. What do we know about Q in the first state? It says here, well, Q is, so that has no operator, so it means it's in the first state. So Q also needs to be true in the first state. What do we know about the second state? It doesn't matter, right? Because nothing talks about Q in the second state. So that's like, let's put a star as a, we don't care what it is, right? And then this thing kind of unfolds infinitely. So how many different traces are there? If I wanted to write down trace computations like that, how many different ones can I write down? One. We can definitely write down one, right? So what, a simple one is the pi2, which is pq in the first state, and then p. So let's forget about all the q's, right? And so on. So that's definitely one. Can we construct more traces? Yeah, by mixing in a q, right? At any of these positions, or at any two positions, or at any three, or so there's infinitely many traces. So even though this formula is looks like it determines everything, there's actually infinitely many traces, right? So how do we now make sure, or how do we check now whether the other formula is satisfied or violated? So if we find a single trace where this formula is violated, we're fine. Or if we can show that for all traces, the other formula is also satisfied, then we basically answered this implication positively, right? So globally, finally, what about globally, finally, P, was it P or Q, right? P or Q. Now, let's look at this. Globally means for every point in time that we pick. So let's pick, I don't know, number 1. Do we see that there is a time in the future where P or Q holds? So let's take even the same one, right? The future is now, so let's take 1. In state 1, does P or Q hold? Yeah, because P holds in every state. So this means that every trace that satisfies this formula here must also satisfy the second formula, because in every state we have P. This means we can always find a next index where P or Q holds, because P holds everywhere. So yeah, this second implication is correct. So we have that Q and globally P implies globally finally P or Q. Actually for this we don't even need we can even weaken this. We can even just say globally P, of course, satisfies that globally finally P, right? Okay, good. So yeah, these things are, we could have now unfolded them to the exists some index where something holds, but I guess we can skip that. And now that we understand the logic a bit, let's look at a tool that helps us automate all this. Because then we don't have to do all these things ourselves. Let's check. Oh. Should have opened it. Yeah, now, so were there any questions about temporal logic, or we can just move on with the stuff that automates all this and solves it for us? So let's have a look at now our next tool, model checking. So what's model checking about? The idea is we get some model of a system and we get a specification. And then we have a tool that tells us whether the model satisfies the specification or it tells us that it doesn't. So it either says, yes, your model satisfies the specification, or it doesn't. So now that we had temporal logic, the question is, what do we take as a specification? And yeah, LTL, right? So we're going to take LTL as the specification. And now what do we take as the model? Well, what was LTL defined on? We defined the semantics of LTL based on transition systems, right? So we now need our model to be transition systems. So we need to express the systems that we want to verify using model checking. We need to express them as transition systems. And we will see that sometimes the transition system will satisfy the model, and sometimes it won't. And then we will get some hopefully informative output why it does not. And we will see that that actually works and is quite important in practice. So the tool that we're going to look at now, this is NuSMV or nuXmv. That's basically, in terms of the history, there was the symbolic model verifier, SMV, which was a commercial tool. And then at some university, they decided, well, let's make a new tool, a new implementation that is not commercial, that's open source. So they basically built this new symbolic model verifier, nuSMV, which is open source and actively supported for, well, yeah, I mean, they're still maintaining it, but now they have some substantial user community, and they provide a language to describe models, and of course, then an implementation to write LTL specifications. So the models that they support are those transition systems, and we will see that they have their own language to describe those models. And this language, we basically have two languages now, because we have the language of LTL, right, the logic that we looked at, and we have a language to describe those kind of transition systems. And we will see that already that language is also not so trivial, but we will see how to use that language today. And this tool, this nuSMV, new symbolic model verifier, then can check the validity of linear temporal logic and also these other computation tree logic formulas on the models. And it will tell us whether the specification holds. So it will simply say, yeah, true. Or it will output a trace, which is some computation, an infinite sequence of state labels that violate the formula. And then we'll say, well, this is false because here is your counterexample. And then I already, indicated on the first slide that there is not only nuSMV, but also nuXmv. And nuXmv, that's now kind of maybe something that's going to replace nuSMV. It's not 100% sure, but it's like the new version of it. And it has some basically extension on top of nuSMV. So in the finite state case, which often is the case that we only have finitely many states, they have some efficient new SAT-based algorithms, but we will not really see those algorithms because, well, we know SAT, but even looking at those algorithms would be quite complex because there's, again, some clever encoding of that in SAT. So we can imagine that this exists because we know SAT, but we probably, the details are probably very technical. And then there is the infinite state case, which is very interesting. Infinite state means basically you could support something like unbounded integers. So in Alloy, we would always have those kind of finite size of sequences of instances where we would say you can have at most this many atoms, and your integers, they go at most from -7 to +8 or something like that, right? But they have some extension in the model checker where they also solve the infinite case, which is new. This was not the case in NuSMV. There, the state space would always have to be finite. The sequences can be infinite, but the states, they have to be finitely many. So they have an SMT-based verification, which is then based on MathSat, so not Z3, but MathSat, another SMT solver, again, which has a very similar language like this SMT-lib. So it also supports SMT-lib. And when you manually encoded stuff, you used SMT-lib language, and you can just put that into MathSat as well. So this one, both of them are free for academic purposes, so we can use them for teaching and evaluation. I think there are some limitations for commercial usages of nuXmv. So if you want to use it, check the licenses. NuSMV source code is available if you want to run it on your machine, and there are no binaries. For many systems, there are binaries. So if you have some standard Linux or Windows, maybe Mac, then you can probably get the binaries. If you have something which is not yet supported, then you have to download it yourself. For nuXmv, I think the sources are not available. So it's a different model, a different license. So all we're doing here, both are basically the same. So nuSMV is a subset of nuXmv. So nuXmv only extends nuSMV. So everything we do, you can do with either one. Okay, and actually in the playground, the one that is running now is the nuXmv, just because they are so similar. So in the slides, I will mostly say nuSMV because we're not using any features of nuXmv, but the binary running in our playground, that's actually nuXmv. And there's really no difference for the examples that we have. There are some stuff that only nuXmv can do, but what we do is just let's say the subset that is supported by both. And the SMV language, of course, we need some language that not only gives us LTL, but also gives us a way to specify models. So we need some language elements in this nuSMV language for models, and then, of course, the language elements for specifications. And there are some, let's say, convenient extensions. So, for example, in LTL, what are the kind of variables that we could have? If you remember, we said there is this set of atomic propositions. Atomic propositions are Boolean variables. If we want to model systems only with Boolean variables, that's like going back to modeling everything with a SAT solver, right? And then we saw that actually SMT solvers with more richer types of variables are quite nice. So nuSMV also has extensions of the language that allows you to have richer types. So you can also have arrays, integers, stuff like that, but they will always be bounded because that's what the language supports. And then for the specification languages, there are some support for LTL, CTL, and also another one called PSL, which is some industrial language, which is a lot larger than LTL and CTL. So it has a lot more language constructs. Some language constructs, they will be equivalent to other language constructs of LTL and CTL, and some, they go beyond what you could express in LTL and CTL. So there are some properties which are not possible to express either in LTL or CTL, but you can express them in PSL. But they are, yeah, quite similar. So if you happen to use PSL later, then your knowledge of temporal logics with LTL, you can apply that directly. Okay, so what do these programs look like? They can be written in modules. The first module, or one module, must always be called main, and that's where you describe your main transition system. But it has modules that you can compose. So you could describe like sub-modules of your system in individual modules and then compose them in main modules. So this way you don't have to replicate many things. So let's say you have a system which has, I don't know, 4 different control units, 4 different parts of a car. I don't know, one that measures speed on each wheel or something like that, and it's a bit more complicated. Then you could simply define that once and instantiate it 4 times in the main module. We're not really going to use a lot of those modules, so we will just always use the main module because we have to. But the systems that we model, they're usually very small, so we don't need to instantiate multiple modules, but sometimes it makes sense to do that. And there is support in SMV to do that. And the main way to define these systems these transition systems is to work on variables directly. So the transition systems that we had here as examples, what we would define is we would define states and then we would define variables. So we would say, well, these are our states, they have some labels, and then we have some variables in them. And these variables, they have some special meaning. And we can assign, of course, changes to these variables by saying, if it's here true, then there it's false. This would be like a state change. And in SMV, you are basically defining just variables, and they can be anything. They could be just labels for your states, but they could also be inputs, they could be outputs of your system, and it doesn't really distinguish. So we will see how that works. So we don't need to maintain a list of states and a list of variable assignments. We're doing everything just with variables by assigning values to variables. And then, of course, we need to give some initial values to variables. And, well, we need to say what might be the next value of variables. So we have basically 2 main keywords, the initial and the next, where we can say, well, the next value of this variable will be some expression depending on, for example, the current value of other variables. And then the modules that we compose, they are basically the models that we model check. So the main module always defines the model that we give the model checker. If we write some LTL formula, it is always evaluated against the main module, which is an instantiation of all the other modules if we have multiple. For us, it will just be an instance of the main module because we will only define the main one. Here is an example. So module main, then we define variables. So we have a request variable, which is Boolean, which says, is there a request or not? And then we have a state variable, which now is just an arbitrary name that we picked, and we called it state because it's maybe the state of our system. Our system is either ready or busy. So that's an enumeration, and this variable state will always have either the value ready or the value busy. Then these are the assignments that define our transitions in the transition system. So the initial state, we say we are in ready. And then the next state, we do a case distinction. Either if there's a request, then the system will go to state busy because now it needs to work on that request. And this true means basically otherwise. So it's like a case distinction. If there's a request, go to busy. If it's true, we don't care what to do. We don't care what other properties might be true. Always do any of these. So this is already pick either ready or busy. And this would be a model. Now, the var, that's basically defining variables with a name and a type. Then there are different variable blocks. We just saw the var, where it's the regular state defining variables, which are the most common ones. There's also something called ivar, which could be input variables, and then you cannot do some assignments to the next value of that input because the input is generated by the environment and not by us. But it's not so common to use ivar. Mostly you see var being used. And then there's frozen var, which means that these variables, they will get some initial value, but this initial value that they had, this remains the value of the variable forever. So it's like maybe some initial configuration that is given to some machine, and that stays with that machine forever. It always behaves according to the initial configuration. There are different types, so Boolean variables, enumeration types, those two we already saw. Then there's bounded integers and arrays. And here are some examples. So the request variable was Boolean, which means it can either be true or false. Then the state variable could either be ready or busy. That's an enumeration of 2, but you can, of course, do more values. Then integers, they must be, again, bounded. So we could say we want integers in the range from 0 to 100. Then arrays here, they have a bit of verbose way to define them. So we say it's an array going from 0 to 7. So the first dimension basically can address from 0 to 7. And then we can have a higher dimensional array where we can then say, well, and then the second dimension can go from 0 to 7 again. And the type of each element in the array is Boolean. So we basically have an array from 0 to 7 of arrays from 0 to 7 of Booleans. And that's like a chessboard, right? That's an 8 by 8 chessboard that's defined by this array here. Yeah, similarly, you could define some, let's say, position. If you want a position on that chessboard or on that grid as a robot position, they could define that's an array with the x coordinate at 0, the y coordinate at 1, and then each coordinate can go from 0 to 7, right? Because we are somewhere on that grid. So this would be yeah, an array of integers. Okay, so all of these are, of course, yeah, linked in the playground, but there's not much to do here because you can't really execute them. They're not doing much, right? So you have the links to inspect them and play with them, but you can't really run them. We will see some more interesting ones to run. Yeah, so yeah, let's look at this one. This one uses some interesting functions. So it's like a vending machine where we have a sensor that says there's a coin right now. In the current state, there's a coin, and then we have an amount that counts the coins, right? So what's going on here is we say in the assignments that the next amount is simply the current amount. So here we have it wrapped in the next, which means that it's in the next state. So whatever state we're in the next state, the value of amount will be the current value of amount plus toInt of this Boolean variable. And well, that's like you would expect. If it's false, the toInt makes 0 out of it. If it's true, it makes 1 out of it. So let's load this. There's one thing. So Shoaib has been working on nice features of the playground. I don't know who has seen it. There's a login feature now. So you could log in with GitHub or Google. And then the nice thing is that you have a history. So you can see all your specs that you've been, well, yeah, okay. So all your specs that you've been working on, and you can also search. See, do we find the coin one? So they only appear here after you executed them. So the permalink one, that's another one because I didn't execute it yet. That's why it's not in my history. And there's a bug. So you might see there's no syntax highlighting right now. Very ugly. If you change to some other language and then back then you get the syntax highlighting. So I don't know. He's trying to fix that bug right now. So if you load it from permalink, it doesn't have the syntax highlighting. But if you switch to another language and then back to that language, you have the syntax highlighting. Yeah, okay. Okay, so let's write a simple LTL specification for this. What would this mean? That's the lines that we had where we say we're updating the amount. Yeah, let's make it. Oh, and we have a full screen feature now. Yeah. So what does this LTL formula mean? So that's we can maybe it makes it helps to put some parentheses. Oh, that's even. So what would that formula on this model mean? Globally, finally, what was that? This means that at every point in time, there is some future where there's a coin. So this means that we get a coin, we get a coin, we get a coin. We might get stuff in between, right? But eventually there'll be a state where we get another coin. So we only can get coins when we have this amount. And then we say, eventually, the amount will be 5. So this means if we keep on getting coins, then we will have a state where the amount is 5, right? So if we run this, is it going to say it's true? Let's run this. And let's see what happened. There's an error in line 6. Cannot assign value 6 to variable amount. Let's look at line 6. Why would it want to satisfy 6 to amount? Amount can only go to 5. But what could happen is that we have to have infinitely many states, right? So if we are in a state where amount is already 5 and coin is still true, then it tries to assign 6 here. So yeah, that's not good. So I think one way to fix it is we can say the minimum of 5 or something like that, right? So we can say if that thing is larger than 5, then just take 5. Then we run it again, and it says the specification is true. Very good. So yeah, and then if we say, well, what about eventually 1? Are we going to get there where are we going to get a state where the amount is 1? We check it. Something happened. So what happened? It says that is not true, false. And then it says it's going to give us a counterexample. It's going to show us why not. And the first state, the initial state of this counterexample, starts with the value of coin being 2. Because we didn't define any initial value for coin. So if you don't define, that's a very tricky thing in this declarative specification of transition systems. If you don't define what's the initial state, it will make one up, and not necessarily the one you want, right? Because it tries to check, does your constraint always work? And if you say, I don't have any restrictions on the initial state, then it tries to find a way to break your system because you want to make sure that your system can't break. Okay, so let's fix that and say we initialize amount as 0. Let's see if that's the right syntax. No. Okay, so we need to, because it's an assignment, we need this assignment with the colon equals, because it's not a statement, it's an assignment. So in a regular formula, it would be just an equals, like here we say amount equals 1, but in an assignment, it needs to be that one. Okay, now the specification is true. So if there's always eventually some coin, then we're going to end up at amount 1. Okay, so here, yeah, the issue is here where that we have a bounded integer size, so we need to do something like the minimum between 5 and between the bound here and what we actually want to add. Okay. Now the state transitions between states, we define them with these assign blocks. That's one way where we say the next value is always amount plus that thing. There are other ways to write this. So we could write it with this next amount equals or is assigned to. We could also do case distinctions. So let's look at a case distinction. Here's our syntax highlighting. So in this case distinction, we say if there's a coin and the amount is less than 5, then the amount is updated by +1. If the amount is 5, then it's updated to 5. And otherwise, it's updated to amount. So there are like those, some cases here. And then if we check again, are we always eventually getting, if we get always eventually a coin, are we eventually getting to a place where amount remains at 5, right? And it says, yeah, this specification is true for the system. Now with this case distinction instead of the other one. The case distinctions, the way you write them is always the condition and then the value inside this case and, case reverse block. And the important thing is that the values are assigned in the order of the matching conditions. So if this condition matches first, it will assign 5. If this condition matches first, it will assign the amount +1. And if that condition matches first, it will assign the amount. Now, if we switch the first two lines, so let's just switch those two, right? Because it's all these cases. Are we going to see any difference? No. We're not going to see a difference. Why not? Because that's not the one that I wanted to show. This is the one that has the difference because here we had amount equals 5, then we remain at 5. Otherwise, if there's a coin, we increase the amount by 1, right? So that's our that's a different one where we don't have this max or min update. And here it's true. Now, if we change the order of those lines, then we should run into trouble because as soon as we have coin, we try to increase the amount by 1, even if the amount is already at 5, because that would only have been checked here. So let's run that one. And now, maybe I didn't run it. Okay. And now it says, well, cannot assign 6 to variable amount because now it matches this one first, this line first. So what we actually want is we want this kind of guard of not overflowing the variable. We want this should be the first thing to happen, and only then we want the increase to happen if that guard didn't catch the overflow. Okay. So the order, yeah, does matter, and that's why we can write the true here at the bottom, because that catches all the other cases. It's like the else case, because if that happened before, then it's this value. If that happened, then it's that value. And in all other cases, we don't care, and oh well, the guard, the condition here doesn't care, and it's just sets it to the amount. Okay. Then another thing that we can see that we already kind of noticed in the initial state is this non-determinism. So if we don't tell it what the state is, then it can pick any. It will consider any, because sometimes that is actually the way we have to implement things. If we have stuff like input sensors, then we might know that some values are not possible, but maybe there's a car coming, maybe there's no car coming, and we can't determine that in our model because the model doesn't know yet. So it has to consider all cases. So we actually need this non-determinism. It's not like a bad byproduct. It's something that we essentially need because we can abstract the implementation of our system, for example, by saying, I don't want to give the detailed specification of that function. Just assume that it might return a value between, I don't know, 1 and 5, and make sure the system still works. And if that works, then we don't have to give the details of the implementation. If it fails because this value is breaking something, then we might have to add the details of the specification and say, well, in this case, it actually wouldn't give you the 5, it would give you the 1. But we only have to add these details if our model checking fails. So that's abstraction and refinement that usually is based on non-determinism. And of course, if we model the environment, then there clearly will be non-determinism because we don't know how the environment is going to behave. So here's an example of this kind of non-determinism that was already in our initial example. We have this request. This would be controlled by the environment. Then our system will say, well, yeah, we're ready to continue working, or no, we're still busy, we're working on that request, right? So initially, the system is ready so that it can take requests. Then if a request comes, the system will be busy. And otherwise, it can either stay busy, so it will keep on working on that request, or it will say, well, I'm now ready again. So it could happen that there's a request and the system stays busy for 5 time slots or for 10 time slots. Or for all time slots, right? It could be. And this would be the non-determinism because we don't know how long it might work on a request. And this would be a possible transition system here. So if a request is coming, then in the next state, we have to be busy. So all the successors here have to have busy. So these are the possible successors of the state with the request, and they have busy and busy. This one here has, again, a request and itself as a successor. So there it's busy. This one as a successor, there it's busy, and that's the two successors it can have because they only will differ in whether request is true or false, right? So how many states can we have with those two variables? Everything that now we don't have a distinction between state and variables. So every valuation of a variable will be a state in our transition system. So this means there are two possible values for request, true and false, and there are two possible values for state, ready and busy. So this means we have 4 states. If we have some, let's say here, this would be 3 possible states, then we would already have 6 because it's 2 here and 3 there. Now, they might not all be reachable from each other. It could be that there are some states from which we cannot reach another state. But yeah, that's fine. The system could still be defined like that, and then the LTL formulas would only work on the computations that they can do inside the transition system that we defined. Yeah, and here those are quite a lot of transitions that we could do. So we could have a request and stay busy the whole time. Because there's a loop here, so if we continuously get requests, then we will always stay busy. Okay. Then for initial states, we already saw how to define that. So for example, here in initial state, we can say it's ready. Or here for the amounts, I think that's what we did in the example with the coin. We can simply say, yeah, initially the amount is 0. And then there's something, there are basically 2 styles in SMV to define transition systems. One style is the one that we saw with assignments. We will always say the next value of this variable is assigned as that. But now there's some other one where it's based on constraints. We have transition constraints. This is another block. It's not the assign block, it's the trans block. And the trans block would give us a constraint on possible transitions. So we're not giving individual assignments. We just write a constraint that says, for example, the next robot position minus the current robot position, the absolute value of that, so the largest possible change from the current time step to the next time step is less or equal to 1. So this means the robot could stay at the current coordinate, or it could move by 1 to the positive side or by 1 to the negative side, right? So it's the absolute value of this difference is less or equal to 1. So if we have a description of a grid where both in the 0, so let's say 0 is the x-axis and 1 is the y-axis, then it says we can move by maximum 1 left or right in the x-axis, or by maximum 1 up or down in the y-axis, but we could also stay in the space. We don't know how the robot will move, but these are possible moves that it could do. So it also could go diagonally, right? Because then it increases in both, then it's diagonally. And then we could say, well, there are some transitions where we need to make sure that the grid position of the 2 robot coordinates in the next state is, well, true. So if we have a grid of Boolean values, then being true could mean that this is a field that the robot can visit. And being false means maybe this is a wall. So the robots, this is a further constraint on the robot. It says the robot can only move. The next positions must be on fields in the grid that are true, so that are a field where the robot can actually move to. Yeah, this would be the explanation. So here, yeah, grid x, y of the robot, but now, of course, this x, y of the robot position, we encode it as this array that must be true. And let's have a look at this. So this is a bit more, it contains what you saw, but it contains a little bit more. It has this, for example, some constant for how large is the grid. Then it has this 2-dimensional array of Booleans. So it's basically this grid, which has the x coordinate, the y coordinate, and then it says, well, that's a Boolean one. And this is actually a frozen var. So the grid doesn't change over time. Initially, it will be determined what is the map that the robot has to move in. And then from then on, in every state, the map stays the same. The robot can just move its position. And the robot position, that's again here encoded as an array 0 to 1. So x and y coordinates of something on this grid. And then we have this change of coordinates as a constraint. As we saw before, they can change by maximum 1. And the robot can only move on fields that have the value true. And then we have an LTL specification that's a bit tricky. So we're basically saying it's not possible that the robot is with the x coordinate at position 0 and eventually reaches with the x coordinate the max position. So this basically means we're saying it's not possible for the robot to move from the left of the grid to the right of the grid. So what happens if we analyze this? What will the model checker do? The model checker will check whether this is really not possible on all grids, because we're not restricting the grid, right? So if it finds a grid where it would be possible to move from the left to the right, then it will tell us, according to these rules, according to these movement rules, then it will tell us that our property is wrong. And it turns out our property indeed is wrong, because there's, of course, a grid. So this grid is, well, a bit more complicated with lots of walls. The false is always a wall. But you could imagine, we know that the grid where everything is true, that's surely the robot can move from left to right. Here, it's a bit more tricky to see. So let's say the robot position is 0, 3. So let's see 0, 3. Okay, that was a wall. We didn't require anything about the initial state because we said only in the next state it needs to be there. Maybe we should, yeah, we should probably add that. It's a bit slow. Okay, so we want to say that robot. It's actually, we want to say the same as down here, right? That the grid at the robot position. So initially, there we are. The grid at robot position and x and y coordinates must be true. Okay, so where's my button? What happened? Down here. Okay, so now the robot starts at position still 0, 3, and let's look at 0, 3. Yeah, that's true. Now then from 0, 3 in the next state, it changes the x position to 1. So x position was 0, it changes to 1. That's valid to the movement rules. So now we will be in position 1, 3. So look at 1, 3. 1, 3 is true. Yeah, it could move there. Next, it will change both to 2. So it will diagonally move, also according to the rules. So is position 2, 2 a field where it can go? Yeah, that's also a field it can visit. And then it will change position 0 to 3, and that's when it reached the, I don't know, how large is our grid? Our grid is, max pos is what? 4, okay. So yeah, it will then move to the x to 3. So we're at 3, 2. 3, 2 is also fine, a field that we can visit. And then we'll move to 4. And then we are at, was it 4, 2, right? Which is also a field that it can visit. Okay, so it showed us a map where it can actually move from left to right. Because we said it's not possible, it basically showed us, well, it is possible. Here's one example. Okay. Yeah, so that's where we have those init and trans blocks. And then we have the assign blocks. And the assign blocks, they are much more restricted in what you can assign. You could always say the next value of this will be something, either with a case distinction or not. And the init and trans blocks, you just define constraints on these initial states or on the next states. without really formulating assignments. So you're not, like in a programming language, you would always formulate assignments. You say this variable is updated to that value, right? And in a programming language, you usually don't even have the non-determinism. And in the init and trans blocks, it's even worse. You just say there is something that needs to hold for consecutive states, but how exactly that's achieved, we don't know. How the robot exactly moves to move from one cell to the next, we don't define it. It can move in any way that that satisfies the constraints in our init and trans blocks. So usually they allow lots of non-determinism, but often that's desired in those kind of systems because you either want to abstract away some of the implementation details or the non-determinism simply exists in the environment. Yeah, and then of course, to really make use of those specifications of those models, we need LTL specifications to check them. So here, this would be a very simple one for our system that takes the requests and either goes to, well, here it just says, well, it goes to ready directly. Okay. And then here it says, if globally we have a request, then eventually we'll be in a state where we're busy. So is that LTL formula going to be satisfied? Yeah, if we get a request, of course, we immediately are, the next state will immediately be busy. So looks like this one should be satisfied. And yeah, it says it's true. Good. Now, if we have something that is not satisfied, so if we, for example, want to state that globally, finally, we're going to be in a state that is ready. So let's change this to globally, finally, state is ready. Is that going to be satisfied? So this means, can we infinitely often be ready, right? Because globally, finally means at every point in time, there is some future point where we are ready, where the system is ready. Why not? Sorry? So what could happen? Let's check what could happen. It says, yeah, this thing is indeed false. We could get a request. Then we have to be, well, let's say initially we're ready and we get a request. Then in the next state, we have to be busy, right? Because we got a request. Now, what is the value of request in this state? We don't see it here, right? But this is a computation, so there must be a value. Okay, what they do is to not make the counterexamples too long is if they don't repeat it, it means it remains the same as in the previous state. So request remains true because we don't update it. So there's the difference between the non-determinism in the models and the actually concrete counterexamples. So they always have all variables assigned. So the initial states will define all variables, and then each successor state will only update the variables in the way necessary just to not print too much. Okay, so state busy and request is true. Then that's where a loop starts. We have to go to another state where the values remain the same. So in this loop, state remains busy and request remains true because we're not adding any new assignments. And that loop goes on forever. So there's basically, it's a bit of strange notation here, but there's basically two states in the loop and they just remain with the same assignments. So we're reaching a loop where we will remain busy forever because requests are true forever. And remaining busy forever means we're not satisfying this. So if we are in an infinite loop and this infinite loop never has state equals ready, then of course we can't have state equals ready infinitely many times. Okay. So that's the way to read those counter examples. We have the initial states, and then it only lists the updates of the values, but everything else remains of the value that we had seen it. Yeah, and then of course here, if we have non-determinism, it gets a bit more, yeah, well, it just remains the same. We just have potentially more traces. So here, if a request comes, then we will be eventually in state busy. Is that still going to hold? So the difference here is that here we had to go back to ready. Here we can stay in busy. But that's what it's asking for, right? It says eventually there'll be a state busy. So whenever we get a request, yes, we have to go to busy. So this will still hold. So for both, this property will be valid. Just run it quickly to confirm. Yeah, also here, although it's non-deterministic, the property is still true. Okay, yeah, and I think the next one we will continue with on Friday. I think the plan is that we will release the next assignment on Friday, but we still have a few slides to finish here, a few examples that will help you with the assignment. So I think we still have 10 slides here. So we will continue those remaining 10 slides on Friday, and then you will get the assignment, and you will see that some stuff will be on the assignment that is very similar to, like, for example, you will check LTL equivalence with the model checker as part of the assignment. And yeah, that's why we will do that still on Friday, those last 10 slides. And then you'll get the assignment, the new assignment on Friday. Okay, so yeah, see you on Friday.